the intermolecular forces, hydrogen bonding. Now, the evidence of hydrogen bonding, how can we show that there is some related hydrogen bonding is there? First of all, we will think about the molecular size of simple hydrides. That means hydrogen-containing compounds. Hydrides of group 4 to group 7 elements. We find that the molecular sizes of simple hydrides should be increases down the group. The boiling points are expected to increase down the group as well. So CH4 is the lowest boiling point, SiH4 greater, GH4 even greater, and then SNH4. It will be more greater molecular size. As a result, their boiling point should be getting higher and higher. This shows the intermolecular force is increasing. However, we found that when it is for the group 5, group 7, group 6 case, we found that the boiling points are different. So although the group 4 hydrides, the trend is fulfilling what we expect. The greater the molecular size, this is the molecular size using molecular size increase, and then the Van der Waals force increase. So the boiling point increase as well. As a result of that, we see that for the group 4, it fulfilled the trends. But for group 5, group 7, or group 6, the odd out one are these three. We found that this one is still fulfilling this kind of trends. However, for H2O, HF, or NH3, they are out. They are strange. So here, it implies the molecular size greater and then Van der Waals force greater as well, or the London dispersion force greater as well. Hence, it affects the boiling points. However, for H2O, HF, and H3, it should be something not the Van der Waals force can explain. As a result, it should be some forces stronger than Van der Waals forces. We say that this is a kind of hydrogen bonding exists in H2O, NH3, and the HF. So due to the hydrogen bonding presence, the abnormal high boiling points occur for these three compounds. They are unusually strong attractive forces between their molecules. These forces are saying hydrogen bonding. The formation of hydrogen bonding, we see that when a hydrogen atom is directly bonded to a highly electronegative atom, a highly polar bonds will be formed. So the hydrogen, when it is attaching to fluorine, hydrogen attaching to O, hydrogen attaching to N, the bonds are highly polar. It is not saying it is the general polar one. It is highly polar. So the bond pairs of electrons will be drawn even more closer towards the highly electronegativity atom due to the larger difference in the electronegativity. So this makes the hydrogen atom carries a positive charge and even more positive than expected. And its nucleus is relatively unsheltered as it has no inner shell. As we can see for the electronegativity value, the hydrogen is 2.20 and fluorine is 3.98. While fluorine will attract more electrons to itself, so it is more negative, delta negative and delta positive. As F, O, N are the three highest electronegativity element, so it can form hydrogen bonding like this way. There are electrostatic attraction between the partial positive charge and the lone pair of electron on a highly electronegativity atom of another molecule. Now, this time it is not only attracting with the delta positive and the delta negative. In fact, it seems that the electrons are going to another hydrogen. You can see from this animation, the electrons are going to another hydrogen instead. So that is, for example, for the case of HF, it is no longer using the delta negative to attract the delta positive instead. It is using these lone pair electrons to attract the hydrogen so that it will form the electrostatic attraction, that is the hydrogen bonding. Hence, this kind of force is the hydrogen bonding. The electrostatic attraction are named as hydrogen bonds. So we can illustrate with the hydrogen fluoride molecules. This is a very positive, and the following is very negative, as it is very electronegativity. So the hydrogen bond, where is it? It's the lone pair electrons in the fluorine attracting with the hydrogen atoms. So when fluorine atom being small enough to approach very close to the hydrogen atoms in the neighbor molecules, then this kind of force attracts with each other. So the fluorine lone pair will attract to the hydrogen instead. The fluorine atom, when it is having the lone pair, it cannot attract the hydrogen in the methane because like this kind of attraction doesn't exist because this hydrogen is not positive, it's not delta positive. So it is only exists in HF and another HF. For CH4, as this one, it doesn't contain any delta positive, so it has no hydrogen bond at all. For the formation of hydrogen bonds in the hydrogen fluoride, no longer delta positive attract the delta negative. In fact, it is the lone pair electron, and the lone pair electron attracts the hydrogen atoms instead. So these lone pair electrons overlap with the hydrogen shell and then it forms the hydrogen bonding.